Hello. In this lecture, we are going to continue with the series on the basic real analysis. And as you're aware that we were doing basic real analysis, and it has been quite a while that the lecture has not been, I've not been able to take a lecture. But today, let us start with again basic real analysis. And as you're aware that we have taken an approach where we are building this particular topic keeping problem-centric approach. So what we are doing problems. We are trying to develop this theory using problem-centric approach. So quite often you might have seen me skipping the proofs and everything. Probably I'll take probably 2 or 3 lectures on proof writing as well. But right now my basic aim is to make you proficient in handling the problems at first. Okay. So till now we have done convergence of sequences. We've seen that if I say that my sequence is convergent, let us say if I say that my sequence is convergent, then a unique limit exists. Okay, so a unique limit exists. But if I say that my sequence an is convergent, then limit n tends to infinity an exists and it exists uniquely. Okay, this is the first thing that we have done. Okay, if I say that my sequence converges to L, it implies what? It implies that there would come a natural number n naught beyond which the distance between an and L can be made as small as possible. When I say as small as possible, it dictates me a tolerance limit. So let's say if I'm saying that if my sequence an converges to L, it implies that distance between an and L can be made as small as possible, isn't it? See, if I'm saying that my sequence is converging towards L, it implies what? That the elements of the sequence will be quite close to L. Okay? After a while means what? After some natural. Okay. So let us say I'll take an example and make you understand this particular fact. Okay. So how would I explain this particular thing? So let us say if I'm saying that limit n tends to infinity is 1 over n is equals to 0. What does it imply? It implies that 1 upon n minus 0 distance can be made as small as possible. Okay. When I say as small as possible, this is some given epsilon. So obviously, one has to understand that if I'm saying that my sequence is convergent to the limit, it implies the distance between the elements of the sequence and the limit itself, this distance should become as small as possible. So let us say if a student says that, okay, sir, can it not be possible that I will believe you that this limit n tends to infinity 1 upon n is equals to 0 if you tell me that distance between 1 upon n and minus 0 can be made less than 10 to the power minus 15. So I would say, okay, you are saying that distance between 1 upon n and 0, if I can prove that it is less than 10 to the power minus 15 after some natural number, then a student would believe. So let us say, I would say, okay, you have given me an epsilon. Now wait for a minute. What I'll do, I'll say that take n greater than equals to 10 to the power 15 plus 1. So this is your n naught, and this is your n naught beyond which an and 0, the distance between an and 0 can be made as small as possible. And here as small as possible has been quantified as 10 to the power minus 15. Okay, so please understand this epsilon del approach is very important for at least TFR and exams like these. Okay, so you should, I think you should pay enough attention to this particular concept also. Again, I'm reiterating, if I say that my sequence an converges to L, it implies what? Distance between an and L can be made as small as possible. When I say as small as possible, what is as small as possible? That is epsilon. Now, if let's say if somebody asks me that can I make this distance less than 10 to the power minus 100, I'll say yes, you can indeed make 10 to the power minus 100. I will provide you some natural number n naught, beyond which, if you see the sequence terms, like this n naught happens to be the index of the sequence, beyond which, if you see the terms of the sequence, those terms of the sequence and limit L, the distance would be less than epsilon. I have given an example here. That is, if I'm stating that limit n tends to infinity 1 upon n is 0, implies 1 upon n and 0, the distance can be made as small as possible. So let us say a student says that, can I make this distance less than 10 to the power minus 15? Obviously, you see 10 to the power minus 15 is a very small number. So one would believe, okay, 1 upon n and 0 distance, if I can prove that it is less than 10 to the power minus 15, somebody would say, okay, I'll believe you that the limit n tends to infinity, 1 upon n is 0. Okay, so if this is the case, so somebody would believe in this. So let's say, according to his belief, I will give him a natural. Now, if somebody says, no, I would want n naught to be, I want epsilon to be 10 to the power minus 18. So I'll tell him that yes, indeed, I can make 1 upon n and 0 distance less than 10 to the power minus 18, provided I take n naught 10 to the power 18 plus. So if I take natural number beyond this, then all the sequence elements of the sequence and the distance from the 0 can be made lesser than 10 to the power minus 18, which happens to be your desired tolerance. So this is how you define. So if I'm saying that my sequence is converging towards L, so let's say this is your L, this is your L. If I'm saying that my sequence is convergent, what does it imply? It implies that it implies what? An minus L, this particular distance can be made as small as possible. Okay, so to understand my point, time and again, I'm saying this is an important concept. Please understand, this is indirectly or directly asked at quite many exams. Okay, so if I'm saying that the sequence limit is L, then the distance between the sequence elements of the sequence and the limit L can be made as small as possible. When I say as small as possible, how do I quantify this as small as possible? See, as small as possible is quite informal way of saying it. So let us formalize it. So somebody would dictate me some tolerance limit, and I would say, okay, if my sequence is convergent, let's say an is convergent towards limit n, then an and L distance can be made as small as possible after some number n naught. Okay, so beyond this, you see all these elements, n naught plus 1, n naught plus 2. If I take their difference from the limit L, it will be less than epsilon. And I have stated here an example by which you can understand this particular thing. See, this example is an easier example to solve algebraically, therefore I use this example. If you're good at algebra and everything, then you can take different other examples also. And please feel free to ask anything so that this session remains a little bit interactive. So understand my point that if I'm saying that my sequence an is convergent, then an, then my an would belong to L minus epsilon to L plus epsilon for all n greater than equals to n naught. So what does it imply? It implies that, let's say this, I'll make something like this. I'll give it a weight epsilon. I'm showing epsilon here quite exaggerated, but let it be. Okay. So now what will happen? Sequence element could be anywhere, but after I cross this n naught, all the sequence elements are going to be here only. Am I audible or am I not audible? Okay. So all the elements of the sequence will lie in this breadth only, right? In this breadth only. That is in this particular thing. So if this is the case, then I'll say that my sequence is convergent to L. Is that clear or not clear? I mean, is there somebody online or not? Okay, so there's nobody online. Okay, fine. So this is one thing that you should remember. Now let us do a few more. Let us understand it using some example. So let me take an example, and then probably you'll be able to understand this particular fact. So let me give one question, and then you'll be able to understand. Let us say assume that limit n tends to infinity. Assume that limit n tends to infinity, an is equals to 0, and bn is a bounded sequence. Bn is a bounded sequence. Then limit n tends to infinity, an bn is equal to 0. What do you think about this? Okay, I think Daisy uh, is that, I mean, am I audible now? That is fine, I guess. Okay, so how would you approach this question? Say, I'm saying that limit n tends to infinity, an is equal to 0, and bn is a bounded sequence. Then limit n tends to infinity, an bn is always equal to 0. True or false? What do you think the answer would be? Okay, so I'll teach you. Don't worry. This is a simple question. See, if I'm saying somebody says false. Okay, so let me do it for you. What do you mean by bounded sequence? Uh, if I say that B, so the question is quite clear that assume that limit n tends to infinity, an is equal to 0 and bn is a bounded sequence, then I want to find this. So if I want to find this, how would I find this? See, I know that limit n tends to infinity, an is 0. That implies distance between an and 0 can be made as small as possible. Let's say epsilon. Or I can make it as small as possible. This epsilon is an arbitrary number. Right? So instead of epsilon, I can also write something like epsilon by m also. If I'm saying I can make it smaller than any arbitrary possible positive number, then why not less than epsilon by capital M? And why I'm using capital M, I'll let you know. See, here what it is given? Here it is given that Bn is a bounded sequence. It implies what? It implies that Bn modulus can be made less than M for all n belongs to natural. So if I'm saying that my sequence Bn is a bounded one, what does it imply? It implies that Bn modulus is less than M. And if I'm saying that my limit an is equal to 0, what does that imply? It implies that an and 0, the distance between an and 0 can be made as small as possible. So why not less than epsilon by m? Now using this 1 and using this 2. And this can be made less than epsilon by n for all n greater than equal to some natural number. This is what I have taught you. That if I'm saying that my limit of a sequence, again I'm telling, if limit of a sequence is equal to, let's say, 0. What does it imply? It implies that an and 0, the distance can be made as small as possible after some natural number. Let us say n. This is what it means by convergence. See, when we say I am converging, okay, obviously I cannot take example of finite distances and then I can make a sense of convergence. But I am saying that if sequence is convergent to a limit, it implies there would be some natural number. There would be some natural number after which an and 0, this distance will become as small as possible. So I've given you an example that if I'm saying that my limit 1 upon n is 0, then 1 upon n and 0, this distance can be made as small as possible. And if I'm saying as small as possible, it implies that you just give me an epsilon, I will give you a natural number. So you say that, okay, I will believe on you if you say that 1 upon n and 0, this distance can be made less than 10 to the power minus 50. Or let's say somebody would come and say that, okay, I don't believe in 10 to the power minus 15. For me, even lesser number would be 10 to the power minus 18. So you have given me an epsilon. I am in a position to dictate you an n naught, after which you just take sequence, take a difference from 0. You'll find that this is less than the given prescribed limit, given prescribed tolerance. So if this is the scenario, if this is the scenario which I'm indicating, then I would say that my limit exists. I hope is that clear or not clear? Please let me know if I'm not making any sense, because I've done it in the first lecture, but it has been quite a while that I've not taken any lecture. So uh, if anybody has any doubt, please let me feel free to ask. So if I'm saying that limit n tends to infinity an is 0, what does it imply? It implies that an and 0, this distance can be made as small as possible after natural number n naught. Also understand that bn is a bounded sequence, which implies that bn modulus can be made less than n. Now you take this first and this second. I can clearly say that an into bn modulus can be made less than epsilon for all n greater than equal to n naught. You just multiply both. And deliberately, I took epsilon by n because students have this kind of notion in their head that they want to see epsilon. Otherwise, I have no issues. But usually, students have this kind of issues. So therefore, I've taken epsilon by m here. Because if I'm saying this is any arbitrary positive number, epsilon is any arbitrary positive number, dividing it by m will not haunt its arbitrariness anyway. So understand this has been written. It implies what? An bn minus 0 can be made as small as possible for all n greater than equal to n. It implies that limit an bn is equal to 0. I hope I'm making sense. If there is some doubt, please ask. Uh, I don't know who all are there. Bharat is there, Daisy is there, Ishika is there. So does anybody has any doubt? Has anybody got any doubts till now? Okay, should I move ahead? Okay, so this is one thing. Second thing that we were discussing in sequences was monotone convergence criteria. Okay, and what is this criteria? So let's say if I'm saying that my sequence an is convergent, then it implies that it should be bounded. This is fine. Now, if my an is an increasing sequence, then it becomes convergent only if it is bounded above. And if my an is a decreasing sequence, it becomes convergent only if it is bounded below. These two are important things. So what it implies that if I have got a monotone sequence, having proved that an is a monotone sequence, additionally, what I need to prove? Additionally, I need to prove boundedness. If I am able to prove boundedness, I'm done. I'll say that my an is a convergent sequence. Okay, proof probably I'll take a few days later, but understand this is first thing that you should keep in your head, right? I hope it is clear till now. Okay. Now, I'll do a question from, I think, TIFR so that you'll be able to get it. But before doing that question, I'll help you with a few things. The first thing is this. This is called as a monotone convergence criterion. Further, if sequence is increasing and it is bounded above, then your sequence limit an always converges towards the supremum of an. And if sequence is decreasing and bounded below, then it converges to the infimum. Okay, these two are important results. You should remember these two results. Okay, so let us, without wasting time, that if you allow me to take a difficult problem, I'll start with a very difficult problem at first. And if you want a real progression in terms of problem, so I'll take it progressively. So I had a problem in mind. So I'll take that problem at first. So you'll be able to gauge the level of TFR also. So the problem was asked in the sense, I'll directly write the sequence. Okay, I'll directly write the sequence. And the sequence is, if I'm saying this is the sequence. Okay, so just give me a minute, I'll write it for you. So the sequence was, I think, okay, given an. Okay, so this is your sequence an, which is given to be. Let me just give me a minute, I'll write it here. So an plus 1, if I remember, it was an plus 1 is equals to root 2 raised to power an. And it was asked that whether this sequence is convergent or not. Okay, and then there were options also. So we'll cover all those options. But first question that arises is that whether or not the sequence is convergent. Whether or not. And it was given that A1 is equals to root over 2. And it was given that an plus 1 is equal to root 2 raised to power an. Okay, so how to approach such questions? See, understand one point. The first thing that any student should do in the exam, if I'm saying what you can say, if I say that if you want to go step by step, the first thing any student would do is what he's going to try. He's going to try putting some values, right? And this is quite obvious that one would try that, okay, let's say root 2 raised to power root 2. One would do this and he would try, okay, or he or she would try this thing that, okay, root 2 raised to power root 2. So what one can think, okay, anyway, one thing is very much clear that your sequence, elements of the sequence are greater than 1. This is quite clear because see, root 2 is around 1.414 or something of this sort. This is an irrational number. We've proven in this first lecture itself that root 2 is an irrational number. This particular fellow, we're also going to prove that whether it is irrational or rational, but there is a theorem that I want to later on focus. But right now, just understand this is some number, which is root 2 raised to power root 2. One point you can make very clearly that in any case, it will be less than root 2 raised to power 2. This is very much clear. See, and also understand one thing, I'm placing it here itself at the very start. If I'm making the graph of a ki power x and a is greater than 1, then only it is increasing. If I'm making a graph of a ki power x and a lies between 0 and 1, then it is a decreasing function. So never do this thing, never make a mistake of comparing directly. First, think that what your a is. So clearly your a is greater than 1, that is root 2 is what, 1.414. Then you can do this particular thing. Otherwise, you could not do this particular thing. Let's say I'll give you an example here. So I'm giving you example so that you can understand what I want to say. 4 is greater than 3, clear. Now, if I apply 2 ki power x function, which is given by 2 ki power x. So it will be 2 ki power 4 here, and it will be 2 ki power 3, good enough, fine. But what if I use function equals to, let's say, 0.1 ki power x? Now here it is a decreasing function. Now apply. Now here you are going to make a mistake. 0.1 की power 4 is not greater than 0.1 की power 3. So why did this happen? This happened because this function is decreasing. In mathematics, you know that if x is greater than y and if a function is decreasing, then it reverses the order. So these functions are also called as the order reversing functions, and increasing functions are also called as the order preserving functions. So please do understand this point. This mistake usually people make. But right here, okay, that's fine completely. That root 2 raised to power root 2 would be less than root 2 to the power 2. Now you'll be tempted to ask, why am I doing this? See, for any question, the first thing that you should do is start putting some values. Okay. Being a teacher, I know the entire solution. But if what if I am in your own situation? So I'll try to place some values to it. Okay. And I do understand this A2 is obviously less than 2. A2 is less than 2. And this fellow here is also less than 2. And it is again raised to power something root 2. So obviously this number, let's say if I'm saying it as A and A is less than root 2, then I can clearly say that this would be less than root 2 raised to power 2. So again, you see that all these elements that I'm writing, they will be lying between 1 and 2. They would be greater than 1, that is clear, and they will be less than 2. That is again clear. Is that clear or not? Who like Ishika is attending class, Daisy is attending, Bharat is from physics, so I can expect that probably his response will not be that strong. But the people who are in mathematics, please do respond at least so that I'll be able to understand that you're getting or not. Okay, good enough. So this is first thing that you should do. Now you understand my point. This is first thing that you should keep in mind. Now, in order to make this statement even bolder, what would you use? You will use principle of mathematical induction. This is something that you're going to use here at home right now. In exam, it's fine that you've somehow figured out that an lies between 1 and 2. That is fine. In exam, it is fine. But let's say you are at home, you are at peace. Now, if you want to really think over this particular statement, then what you can do? You can really think, okay, let's say, what does principle of mathematical induction say? I am going to write some statement Pn. First, I'm going to check whether it is true for 1, and then I'm going to see whether it is true for n plus 1 or not. If it is true for 1, and if it is true for n plus 1, then I can clearly say that Pn is true for all n. I mean, this is how you prove. So this proof is called as proof by mathematical induction or proof by induction. And this is very important, very, very important for your real analysis part. Okay, so how would I prove? I do understand that whatsoever be the case, an is greater than 0. An is greater than 0. You can clearly see that an is greater than 0. And what is your an plus 1? An plus 1 is root 2 raised to power an. And an is greater than 0, so I can write it as root 2 raised to power 0. So an plus 1 would be greater than root 2 raised to power 0. So I would say that my an plus 1 is greater than 1. This is clear. Now I know that an is less than 2. What would be my an plus 1? An plus 1 is given by root 2 raised to power of an. And I do understand that an is less than 2, so it will be less than root 2 raised to power 2, since an is less than 2. So clearly an plus 1 is less than 2. So what was my claim initial? My initial claim was that an lies between 1 and 2. My a1, which is clearly root over 2, also lies between 1 and 2. And that my an plus 1, I've also proven it lying between 1 and 2. So by principle of mathematical induction, I can say that my an lies between 1 and 2, which implies that my an is a bounded sequence. Okay. Now what additional I need to prove? Additionally, I need to prove that whether my sequence is monotone or not. The second thing that I have to prove is that an is monotone or not. Now, this is a difficult question because see, here you can clearly see that your one element is here and just an element lesser is placed on the power. So usually when I teach my students, I find them taking log and then they get trapped into it and they can never come out of it. So what is my approach? What do I see? Say, always take the help of functions. Standard 12th. Use functions when you get trapped. See, you know this particular thing now, that if function is defined from an interval I to R, and if f dash x is greater than or let's say equal to 0 for all x belongs to I, then you know that f is an increasing function, right? So if at all you are not able to prove directly that whether your sequence is increasing or decreasing, then what you can take, you can use the framework of function. You can use the framework of function. Now you would say that how would I use the framework of function? Okay. See, what do you need to do? You need to compare an plus 1 and a, right? This is clear. It implies that you need to compare an plus 1, sorry, you have to find this value. For all n, if it is greater than 0, then it is increasing. For all n, if it is less than 0, then it is decreasing. In this, precisely in this particular question, you are going to compare this. So basically, it turns out that I am going to write a function f of x, which is 2 raised to power x by 2 minus of x. If I find how this function behaves, then I can make a judgment about this particular fellow. See here, just see both of them. These are both almost, see, this is something where you are having discrete inputs here. So you will put an at n equal to 1, n equal to 2, so a1, a2, a3. And this is a continuous function throughout for all x belongs to 1. Where am I interested? I'll be interested only in this region. Okay, x belongs to 1 and 2. Not beyond that. Because see, what is my region of interest? I understand that each of my element of the sequence are lying between 1 and 2. So I'll only consider the case where x lies between 1 and 2. And I'll consider the function f of x is equal to 2 ki power x by 2 minus x. Now, if I'm able to make some understanding out of this, then I'll say that if it is true for all x belongs to 1 and 2, then it would be true for a n also. I hope I'm making some sense here. Is that clear or not clear at all? So what have I done? I have defined a function from 1 to 2 to r given by, and in fact, you can even take these two. That's not a problem at all. Okay, because you can place 2 here, it's well-defined function. Okay, so you can even take the closure here. But let's say we define this particular function. Is there any problem with the construction of the function? Okay, please feel free to say anything, because otherwise you'll never be able to understand. You'll think that I'm doing some mathematics on my own. Nobody is saying. Okay, fine. So how would I say that this is an increasing function or decreasing function? I'll have to take a derivative. So what the derivative would be? It will be 2 raised to power x by 2, and then I'll get ln of root 2 minus of 1. Now, this is a difficult thing. See why it is a difficult thing. I don't know how this particular thing would behave from 1 to 2. So usually when you get trapped here, see, if you want to solve, I'll solve it for you. It is greater than 0. When it is greater than 0, it is greater than 0 if 2 ki power x by 2 is greater than 1 upon ln of root 2. And only if x by 2 is greater than log base 2 1 upon ln root 2. Now, this is very terrible thing. You'll never be able to find this thing in exam, that what it is. So you'll never be able to figure out in what interval your function is increasing. So at times when you are getting trapped here, what is the way ahead? I'll let you know. The way ahead is to take the second derivative. Just take the second derivative without thinking, even for a second. Just take a second derivative. If you take the second derivative, what you're going to get? You're going to get ln root 2 whole square here. Okay. I think you'll get this only with ln root 2 whole square, and there would be 1 over 2 also. So overall, understand this is positive, this is positive, this is positive. So your second derivative to the function is positive for all x belongs to 1, 2. What does it imply? I'm writing it here. It implies that your f dash x is an increasing function. Your f dash x is in. Okay, so someone says that by taking derivatives to find it's increasing or not, can't we just find some terms like a1, a2, a3? See, I do understand what you're saying, but will you be able to make some judgment from here that it is an increasing function? I don't think so. I mean, it's very difficult. How would you be able to understand that this is an increasing function. I don't get it. But somehow this is something quite difficult in exam. Okay, so the best thing is take some function in order to validate what you are thinking right now. Okay, indeed, whatever you are thinking is right. That you are thinking that okay, the function is increasing, an is increasing, and that it is bounded. Fine, but that would not suffice you in at least TFR, or probably when you sit in the exam. Even if you clear the exam, then internal exam you are bound to fail. So that is why I'm saying this would be the safest approach that I'm saying. And indeed, why I'm taking derivatives in order to understand what will be the interval in which the function is increasing or decreasing. Okay, so let's say if I am not able to make any judgment with first derivative, I'll take a second derivative. I have taken a second derivative here, and I do understand that my second derivative is positive. And if my second derivative is positive, implies that first derivative, that is f dash x, is an increasing function on x belongs to 1 comma 2. So if for all x belongs to 1 comma 2, sorry, for x, all x belongs to 1 comma 2, sorry, if f dash x is increasing, then I can clearly write this way. Okay, so it is going to preserve. And what is f dash? You do understand that f dash is this. So it is 2 raised to power. Okay. And what would be ln root 2? So ln root 2, if you remember in radioactivity, you might have seen that ln 2 is 0.693. And ln root 2 would be half of it. And 2 is here. So it would be 0.693 minus 1. So obviously it is negative. This is negative. And even f dash 1 would be negative. So clearly you can say that f dash x is a decreasing function, counterintuitive to what you are thinking. Okay, so probably students are tempted to say that, okay, I feel that this particular function is increasing, rather it is decreasing. Is that clear? Okay, so f dash, sorry, not f dash. So f dash is negative and fx is a decreasing function. Sorry, since f dash x is negative, since f dash x is negative, clearly you can see that this is negative. I mean, I can write log root 2 is here, so I can place a 2 over this. So it will be log 2. Log 2 is, I think, 0.693 minus 1. This is negative. Here also it would be negative. Fx is a decreasing function. If fx is a decreasing function, for all x less than 2, f of x would be greater than f of 2. Okay, or why should I even write this? Understand that I have proven that fx is a decreasing function. Okay, so okay, f of x would be greater than f of 2, right? Sorry. It implies what? It implies that 2 raised to power, I think it was x by 2 minus of x would be greater than f of 2. If you write f of 2, what it would be? So f of 2 would be 2 by 2 is 1, 2 minus 2, which is 0. So it implies what? It implies 2 raised to power x by 2 would be greater than x for all x belongs to 1 comma. And if it is true for all x belongs to 1 comma 2, what sin these guys have committed? Obviously, an also lies between 1 and 2 only, no? So an also lies between 1 and 2. So if it is true for all x lying between 1 and 2, why not an? So I'll, instead of writing x, I'll place an here. So it implies 2 raised to power an by 2 would be greater than an. And what this fellow is, this is an plus 1. And here you come. Here you come to your assertion that your an is increasing sequence. Okay, so at times it happens that the underlying structure is decreasing, but overall we get that an is an increasing function. So here it's not, sorry, it was not counterintuitive, rather it is in it, whatever you were thinking. Like, let's say there was a child who was saying that if I place all these values, why can I not claim that this is an increasing function? Indeed, probably from an idea you can think that okay, root 2 is greater than 1 and power is also greater than 1. So probably one is tempted to say that this is increasing, fine, good enough. This is good for exam, but in general, I will have to prove this way. Okay, I thought that was decreasing, but the sequence appears to be an increasing sequence. Function is decreasing, And because of this decreasing function, it happens that an plus 1 is greater than an. So mind my words, I made some lapses in between, but overall understand that this is an increasing function. Sorry, this is an increasing sequence. Fx is decreasing, sequence an is increasing. An is increasing plus an is bounded. What does it imply? It implies that an is a convergent sequence. And since an is a convergent sequence, obviously there would be some limit. And what would be the limit? And this is quite difficult problem. So if one wants to say what would be limit, see, anyway, understand if sequence is convergent, this limit must be unique. Okay. And you understand that if an limit is L, then an plus 1 also would converge to L. So it is equal to writing L is equal to 2 raised to power L by 2. And since there is only one limit to it, you can on inspection write this. Otherwise, this is another question in itself. See, this is not an algebraic equation that you can solve very easily. This is an equation which is a transcendental nature. So either you have some numerical methods or you draw a graph. Even if you draw the graph, you'll be able to figure out that, okay, this will have a root, but you cannot figure out precisely what is the root. So little bit of mathematics, little bit of understanding, just place L equal to 2 here. So if you place L equal to 2, you'll get 2 is equal to 2. So clearly L equal to 2 satisfies this equation. So you in exam, you can write clearly that L is equal to 2 would be the root. Also understand that AN is an increasing sequence and AN is bounded by 1 and 2. So it justifies that, okay, L equals to 2 can be the root. L equals to 2 can be the limit because AN is bounded above by 2. And had it been it would have been the supremum of this particular sequence. Okay, it's not even the upper bound, it's the least upper bound. This 2 is least upper bound because limit L is equals to 2. I hope I have made enough sense with this question. Is that clear or not clear? Please do let me know. So this is how TFR has a knack of asking difficult questions. Okay, so okay. Now I'll focus to one more important concept today. Okay. And that concept is regards AM greater than equal to GM. So, and you will find that this particular concept is being time and again utilized. Okay. AM greater than equal to GM. Now you see, if I have n positive numbers, then the arithmetic mean of these numbers will always be greater than equals to the geometric mean. And if I state this for 2 points or 2 numbers, this would be the case. Also, always remember the condition for equality. These two things would be equal only if A1 equals to A2. This is the condition for equality. What equality? That AM is equals to GM. Okay, this is the first thing. And you'll find that quite often in exam it is given, and you'll not be able to even figure out that it has been given. I'll help you using an example. Okay, so again a question from TFR. Okay, I think the question was find the maximum value of e raised to power x and e raised to power 1 minus e raised to power x for all x less than equal to 0. So find the maximum value of e raised to power x into 1 minus e raised to power x for all x less than equal to 0. See, understand one point. If x is less than 0, this is how you'll make the graph. So this is how your e to the power x behaves. And let's say at x equal to 0, this is equals to 1. So you know that e to the power x, so e to the power x lies between 1 and 0 for all x less than equal to 0. So clearly it is a positive real number. E to the power x is a positive real number. Also, it lies between 0 and 1. And similarly, if you want to find 1 minus e to the power x, it also lies between 1 and 0 and 1. So both of these guys lies between 0 and 1. These two are positive real numbers. So I can add them up. And I'll take the help of arithmetic mean greater than equal to geometric mean. So both of them are positive real numbers. I have taken the arithmetic mean of e to the power x and 1 minus e to the power x. I do understand that e to the power x plus 1 minus e to the power x upon 2 would be greater than equal to e to the power x into 1 minus e to the power x raised to power 1 over 2. This is the geometric mean. So from here, it's quite evident that this gets cancelled, that e raised to power x into 1 minus e raised to power x would always be less than equal to 1 by 4. So what do you think the maximum value of this particular function would be? So the maximum value of this particular function would be 1 over 4. And this particular maximum value will be attained at the point where there is inequality. And you understand where the things, where arithmetic mean is equal to geometric mean, it is equals to where your a is equal to b. So here your a is this, and let's say b is this. It implies that 2 e to the power x is equals to 1, or e to the power x is equal to 1 by 2, or x is equals to minus. Is that clear or not? You could have easily done it using your standard 12th approach also, but I have done it using arithmetic mean greater than equal to geometric mean. Is that clear or not clear? Okay, good. So again, now I'll take another example in order to demonstrate the beauty of this particular thing, and then we'll continue all these lectures from tomorrow. So first day, it's a first day, so I'll keep it very less today. So suppose that there is a sequence an which satisfies the condition that an lies between 0 and 1, and an into 1 minus of an plus 1 is greater than 1 upon 4 for all n belongs to natural, then uh, then uh, then what do you think about the convergence? What do you think about the convergence? If these two limits, these two conditions are given to you, what do you think about the convergence? Do you think this would be convergent? Okay, good enough. That's a very prompt response. Okay. So how would you do that? If you can unmute and tell, otherwise, fine. Don't want to unmute anything. Okay. So why do you think that this is sorry, it's bounded in one term? Good. So that is good. That is good. Chalo. So if see, how would I say this is bounded? Yes, indeed, it is bounded. And how do you think that this is convergent? How do you think that this is monotone? See, I do understand that an lies between 0 and 1. So your an plus 1 also lies between 0 and 1 in by induction. And 1 minus of an plus 1 will also lie between 0 and 1. If this is the case, then an plus 1 minus of an plus 1 divided by 2 would be greater than equals to an into 1 minus of an plus 1 raised to power 1 by 2. And you already know that this is greater than 1 by 4. So if I write here greater than 1 by 4, so it would be greater than 1 by 2. Because this is greater than 1 by 4, the root over, so it is greater than 1 by 2. What does it imply? It implies an minus of an plus 1 divided by 2 would be greater than 0. Take this half there. And what does it imply? It implies that your an is, I think, greater than an plus 1. So clearly, an is a decreasing sequence. Further, not only decreasing, it is also bounded also. It is bounded. Decreasing implies what? It implies an is a convergent sequence. And now an is a convergent sequence. Now what I can do, I can find the limit also. So how to find limit? I'll say that if limit exists also, one thing understand, whenever I'm comparing two things, let's say I'm comparing two sequences, xn is greater than yn, then for their limits, I can say this, equal to, greater than equal to. One example, 1 upon n is greater than 0, but its limit is equals to 0. So in general, I can say that if I'm going to say, let's say this is your constant sequence, and let's say this is 1 upon n, then I can say that 1 upon n, limit 1 upon n would be greater than equal to limit this. So if I'm taking limit, then equality can come. So I'm saying that limit an is equal to L, and what I have been given, I have been given an minus an plus 1 is, I think, greater than what? I think it was 1 by 4, right? Now, if I limit an is L, then it will be L 1 minus L would be greater than equal to 1 by 4. If I take limit both sides, then equality can appear here. And if I solve this up, I'll get minus of L square plus of L minus 1 by 4 greater than equal to 0. Or in other words, L minus 1 by 2 whole square is less than equal to 0. Any squared quantity can never be less than 0. It has to be equal to 0. So L is equal to 0. Is that clear? This is easier question. So probably I think this is good. This is fine. Okay. Okay. So we'll do a few more questions. Probably from tomorrow we'll take it up. But let's do one more question. Let's do one more question. And this question is about finding limits. So just try to find limit for the sequence I'm giving. This is the last question for today. Now, if I define a sequence, and how have I defined the sequence? Sequence an is defined by an, define a sequence an such that an plus 1th term is given by 1 upon p minus 1 an plus a upon an raised to power p minus 1. So sorry about this. Okay, so this is this. Otherwise we'll get confused. Okay. Okay, so I have defined this an plus p here, and I want to find limit an. The first thing itself arises that whether it is convergent or not. Obviously, yes, here I've given you a limit, so obviously it has to be convergent. But really, if it, the first thing arises that whether it is convergent or not. But since it is given the question, so I'll not pay much attention to its convergence, but let us try to find the limit of it. Let us try to find limit of it. Indeed, it's a big question. So how would I do? See, देखो, अभी I cannot speak Hindi. So whenever it comes to all these things, now always pay attention to this. See, what it says is, see, for the first thing that I would ask to any of my student is, how many number of terms do you see here? What are the number of terms? So if you see very clinically and with a very close observation, you'll see that there are p minus 1 am terms, 1, and 1 of this term. So in totality, there are p terms. And here it is 1 over p. So whenever it happens this way, always remember there is something like arithmetic mean greater than equal to geometry. Okay, indeed, it is very difficult at the very first instance. But after a while, when you gain certain experience, the first thing that you can gauge from this is that definitely the examiner is trying to you to locate arithmetic mean greater than equal to geometric mean in this question. The first thing that you should do. Otherwise, this will become very complicated. So understand my point that if I want to find limit an, so probably I can do it by saying that let it be L, this is B L, this be L, and probably by some mathematical calculation also I can do that. But I'll first resort to finding whether it is convergent or not. Okay, so this would be my first aim. See, understand an is positive. Why an is positive? A1 is given positive. If A1 is positive, then A2 would be positive because P is belongs to natural, so it is bound to be greater than 1. Because if it is equal to 1, then it does not make sense, no? So if it is greater than, so P not only should belong to natural, but indeed it should be greater than equal to. Okay, otherwise this. So okay, so understand my point. The first point that I'm trying to make is that A1 is given to be positive. What would be A2? A2 would be positive. Your A3 would be positive. In general, I can say that AN is positive. Here, how many number of terms do you see? There are P minus 1 AN terms. Like what I can say that AN has been repeated P minus 1 times here. And there is a single term. So totality, there are P terms. So there are P terms added here and divided by 1 over P. So indeed, this happens to be a structure of arithmetic mean. This is quite clear. Am I making sense or not? Good enough. Chalo. So if you can figure this way, so I'll write once for your sake an plus an plus an dash 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 plus an. This I'm writing it for p minus 1 times plus a upon an raised to power p minus 1. This is 1. So in totality, how many terms do you see here? There are p terms, so I'll divide it by p. So this is arithmetic mean of these numbers. These are all positive numbers. This would be greater than equal to an dash 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 an repeated p minus 1 times a upon an raised to power p minus 1 whole power 1 over p. Okay, remember what the number of terms here, it comes as 1 over p here. It is a generalized arithmetic mean greater than equal to geometric mean. I've written it in the very first instance. What do you think this is? This is equals to what? This is equals to an plus 1. Just think. This is your an plus 1. So your an plus 1 is greater than equal to this an raised to power p minus 1 gets cancelled. So this is. So one thing is clear. An is bounded below. Now, if I prove that my an is a decreasing sequence, I'm done. Then I'm done. Because if I have proven that an is bounded below, and if somehow I can prove that my an is a decreasing sequence, then I'm done. Is that clear? And how can I do so? I already know that my an plus p is given in terms of an. So what is it? What it is? It is 1 upon p. And in bracket, I had p minus 1, an minus 1, plus a upon an raised to power P minus 1, I guess, right? This is how it goes. Okay, so if just see, if I take this P inside, this would be P by P. So sorry, this is I think AN. So one AN would get released. So I'll write AN plus 1 minus of AN is equal to what? It is minus of AN divided by P plus A upon A upon AN raised to power P minus 1. Yes or no? And I think one P would also come here because this is multiplied throughout. So I can take 1 upon P common. I'll take this AN here. So I'll get minus AN raised to power P plus A whole divided by AN raised to power P minus 1. This would be positive, certainly. This would be positive, certainly. What about this? I've already proven that my AN plus 1 is greater than equal to A raised to AN plus 1 is greater than equal to A raised to power 1 upon P. Or I can say that AN is greater than equal to A raised to power 1 upon P, or I can say that AN raised to power P is greater than A. So minus AN raised to power P plus A would be negative. So what does it imply? It implies that AN plus 1 would be less than equal to AN, which implies that AN is a decreasing sequence. Now, AN is a decreasing sequence. AN is bounded below. It implies what? It implies AN is convergent. Is that clear? And where do you think your AN converges? You just take a help of this. So if I take that limit n tends to infinity AN is equal to L, then also I understand that limit n tends to infinity AN plus 1 would be also L. Use this equation, L minus L is equals to 1 upon P, and this will become 1 upon L raised to power P minus 1. And here you have minus of L raised to power P plus A. This goes to L minus L is what? 0. All these things fellows go to 0. It implies L raised to power 1 upon P is equal to A. L raised to power P is equals to A. It implies L is equal to A raised to power 1. So your limit is equals to this. So I hope I've been able to give you some important concepts regarding your sequences. I think it's quite enough for today. And if you keep learning all these things, I'll progress, I'll enhance the speed, and probably it will help you all the more for your TFR examinations and examinations like NBHM, GATE, JSNet, whatever you are getting. Okay, so I hope you might have been so okay. So all these things are well done. So I hope to meet you tomorrow. Till then, take care.